Welcome to lesson 3.3, proving lines parallel. The learning target for this lesson is that you'll be able to use angles formed by transversals to prove two lines are parallel. We're now looking at the converse of the corresponding angles postulate, converse of the alternate interior, alternate exterior, and same side interior angle theorems. So remember that converse is to switch the hypothesis and conclusion. So in our original corresponding angles postulate, if two lines are parallel and cut by a transversal, then corresponding angles are congruent. The converse says if two lines are cut, doesn't say parallel, but two lines are cut by a transversal such that corresponding angles are congruent, then the lines are parallel. If two lines are cut by a transversal such that corresponding angles are congruent, then the lines are parallel. So instead of them telling us the lines are parallel and us making a statement about the angles, they're going to be giving us that the corresponding angles are congruent, and we can conclude that the lines are parallel using this converse, converse of corresponding angles postulate, often abbreviated converse of cap. Now, in this particular picture, that would mean that we would have this angle and this angle given as congruent. If we know that those angles are congruent, then that will force their linear pairs, the adjacent angles next to them that form linear pairs to be congruent. Their vertical angles were already congruent. So all the angle pairs that we already know stuff about would be congruent, which can only happen if the lines are parallel. So it would force the lines to be parallel. The converse of the alternate interior angle, alternate exterior, and same side interior angle theorem all start with this. If two lines are cut by a transversal, in this case such that alternate interior angles are congruent, then the lines are parallel. In this case, such that alternate exterior angles are congruent, then the lines are parallel. And in the last case, such that same side interior angles are supplementary, then the lines are parallel. Our goal for this, or our learning target for this, is not to prove these theorems right now. We'll be doing that separately, most likely in class, but I'll also have a video to review it if you need to. But right now our focus is, if we're given these things, or if we identify any of these things in any picture, we should be able to conclude that the lines are parallel. Or, given variable expressions, we should be able to say, hey, well, if these ones are equal, that would give us an answer for x, and if this value of x is the actual value of x, then the lines will be parallel. So, name the postulate theorem that proves that L is parallel to M. So right now, they're not telling us that line L and M are parallel. They're wanting us to find a way to show it. Well, they've told us that 8 and 6 are congruent, and 8 and 6 are corresponding angles. So since they are congruent, L is parallel to M by the converse of corresponding angles postulate, because the angles that are congruent are corresponding. And that's what the converse of corresponding angles postulate says, that if they're congruent, then the lines will be parallel. Next one says 2 and 3 add to 180. Those are actually same side interior angles. So that means that if those are adding to 180, they're supplementary like we expect them to be, then L is parallel to M by converse of same side interior angles theorem. So here's the trick. Before, we knew the lines were parallel and we looked at the angles and identified them. Oh, they're same side interior. And we've memorized that they're supplementary. So we used the same side interior angle theorem. The theorem we're using is the name of the type of angle. So when I look at this, I say, oh, 2 and 3, those are same side interior. So I know I'm using the same side interior angle theorem. The question is, am I given that they're parallel and I'm making a statement about the angles? And then I'd be using the regular same side interior angle theorem. But that's not what we're doing. We've been given a statement about the angles, and we're supposed to conclude that the lines are parallel. Whenever the conclusion is that then the lines are parallel, we must have the word converse in front of the angle theorem or postulate. Letter C, angles 3 and 7. Those are alternate interior angles. So I can say that L is parallel to M by the converse of alternate interior angle theorem. 1 and 8. 1 and 8 add to 180, but they are not same side interior. In fact, they're a linear pair. Linear pairs are separate from parallel lines. They can be connected to parallel lines, but they have to share a vertex, so they don't even touch line M. So line M could be doing its own crazy thing going this way. These would still be supplementary. So I can't do anything. Can't conclude parallel with just a linear pair, or with just a vertical angle for that matter. So in the next one, when they say 4 and 6, hey, look, 4 and 6 are congruent. Cool, but they're only on, their vertex is on this transversal and line M. They don't even touch that line. That line could be doing other crazy things. Those would still be congruent. So again, I can't conclude parallel based on just vertical angles. 4 and 8, I can make a conclusion about because they have separate vertices. They're on the outside and on alternate sides, so these are alternate exterior. Since they're congruent like I would expect them to be if the lines were parallel, I'm going to conclude that the lines are parallel by converse of alternate exterior angle theorem. Another thing that you will be asked to do is to find the value of x that would force the lines to be parallel. In other words, if I just picked any number for x, let's say 20, gosh, I hope that's not it. Nope, it's not. And I put in 20, then this would be 40 plus 10, which would be 50 degrees, and this would be 60 minus 55, which would be 5 degrees. In that case, angle 4 and angle 8 would not be the same. One would be 50 degrees, one would be 5 degrees. The lines would not be parallel. The picture would look much different than it does. So they're saying what value of x will prove the lines are parallel. So we're going to say when x equals, and I'm putting this at the bottom for my answer, when x equals blank, the lines are parallel by, well, 4 and 8 are alternate interior angles, so this would be by converse of alternate exterior angles theorem, that I would be proving the lines are parallel. Since 4 and 8 are alternate exterior, I could make the lines be parallel by converse of alternate exterior. But for that to happen, 4 and 8 must be congruent. So 2x plus 10 would have, because alternate exterior have to be congruent for the lines to be parallel. So these have to be equal, subtract 2x, add 55. X would have to be 65. When x is 65, the lines will be parallel using the converse of alternate exterior angles theorem. Take a look at letter B. We have angles 2 and 3. Angle 2 and 3 are same side interior. So when x equals some number, then L will be parallel to M by converse of same side interior angle theorem. This is going to be our answer. We have to figure out the value of x that works for that. So because they're same side interior angles, I don't want to set them equal. If those lines are going to be parallel, those have to be supplementary. So 10x plus 8 plus 25x minus 3 has to equal 180, because if I'm going to do same side interior angles, I need them to be supplementary. Just like if I was doing alternate interior above, I need them to be congruent. This gives us 35x plus 5 equals 180. I'm going to subtract 5 and divide by 35. So 175 divided by 35 is 5. X equals 5. So when x equals 5, the lines are parallel by converse of SSIA. try this for letter C. See if you can set it up and correctly write the statement when x equals blank. L is parallel to M by. All right, hopefully you said by converse of alternate interior angles theorem, since 3 and 7 are alternate interior angles in the picture. They make the letter Z. So, since they're alternate interior, I need a value of x that makes those two expressions equal. Subtract x from both sides, x equals 50 will force the lines to be parallel. Proving lines are parallel. We are given that R is parallel to M, L is parallel to M, that's already marked. We're supposed to prove that R is parallel to P. The only other information we have is that 1 and 3 are congruent. Well, 1 and 3 have a connector in the picture, and that is 2. The lines that are parallel I'm tracing in green. So 2 and 1, because they're both touching a parallel line, I can actually use those with a parallel line theorem. Because those lines are parallel, I can actually use corresponding angles postulate here. Can't necessarily use it here. Let's talk about that in a second, though. So my first line is my given. L is parallel to M, and angle 1 is congruent to angle 3. Technically, I should put that second one later, but I don't want to write it out later. I want to get it done here. Because L is parallel to M, these corresponding angles are formed with the parallel lines. So I can actually say that angle 1 is congruent to angle 2 using the corresponding angles postulate. If those lines were not given as parallel, then I couldn't use the corresponding angles postulate. Now, a lot of times people say, oh, 2 and 3 are alternate exterior. Can I just say that those are congruent by alternate exterior angle theorem? You could if these lines were given as parallel. If I trace those angles, they are not formed by two parallel lines. This other parallel line is out of that picture. These two lines are not given as parallel, so I can't use the alternate exterior angle theorem. I can only use the regular theorems when the lines were given as parallel. But I do have a congruency statement here. 3 and 1 are congruent and 1 are 2. What's the connector? Angle 1. 2 connects to 1 because of corresponding. 3 connects to 1 by given. So now that I have those connections established, I can say that 2 and 3 are congruent. Not by alternate exterior angles, but by the connector of 1. So that would be the transitive property of congruence. And since 2 and 3 are congruent and they're alternate exterior angles, that means that lines P and R have to be parallel if those two angles are congruent by converse of, well, those were alternate exterior angles. So it's by converse of alternate exterior angles theorem. So here's an example of how these converses are used in proofs. Letter B, given 1 and 4 are congruent, and given 3 and 4 are supplementary. Well, if 3 and 4 are supplementary, that tells us, or we're going to be able to make a statement about M and N. We're supposed to prove L and M are congruent, are parallel actually. So there's line 1. I'm going to put both of my givens there. They did tell me 3 and 4 are supplementary, so I'm going to write an equation from that. That means that 3 and 4 must add to 180 degrees by definition of supplementary. So I've got an equation established linking 3 and 4. That's awesome. They also gave me a congruent statement linking 4 and 1. So I've connected 3 to 4 and 4 to 1. This one through a congruency statement, though, so I have to write that out as measure of angle 1 equals measure of angle 4 by definition of congruent. Well, now I have two equations, and both of them have angle 4 in them. So I can now replace angle 4 with angle 1. Measure angle 3 plus measure angle 1 equals 180 degrees. This isn't, well, they're not a special set of angles anyhow, but they do, that's not going to help me. That doesn't help me, but that's okay. We're going to stop there because they're not a special angle. We're just going to write that out as definition of supplementary. Nope, that wasn't that's coming from plugging it in, sorry. So it's substitution. Unfortunately, 3 and 1 are not a special angle pair. That's why they must have given us angle 2. So I'm going to connect 3 backward to 2. So now I have 2 to 3, 3 to 4, 4 to 1 to get equations. 2 and 3, doesn't matter whether lines are parallel or not, 2 and 3 are always congruent by the vertical angles theorem. There might be a shorter way to do this proof, but this is what we've got so far. So this means that measure angle 2 equals measure of angle 3, again by the definition of congruence. Now I'm going back to this equation. I stopped because 3 and 1 had no special relationship. They weren't, same side interior, they weren't corresponding, they were nothing. But 2 and 1 do have a relationship, and now I can plug 2 in for 3. Measure angle 2 plus measure angle 1 equals 180. All I've done was take this equation and replace the 3 with the 2. So that's, again, substitution. And now we have an equation connecting 1 and 2. Since 1 and 2 add to 180, I can say that angle 2 and angle 1 are supplementary. And that's because they added to 180, so it's the definition of supplementary. And lastly, I would expect 2 and 1 to be congruent if these lines were going to be parallel, because when those lines, not congruent, that I would expect them to be supplementary, because when same side interior angles are supplementary, the lines have to be parallel, and the reason is converse of SSIA theorem, same side interior angle theorem. Whenever your conclusion goes from a statement about the angles to saying the lines are parallel, you must use the word converse. If I were given parallel lines and I were saying that these are supplementary, then I would be using the same side interior angle theorem, not its converse. So there's some examples of how converse theorems are used to complete proofs. If you're trying to prove lines are parallel, notice that that's going to be your last statement. The lines are parallel by some converse, based on some angle relationship that you were able to establish through your connections. This concludes the video notes for lesson 3.3. If you need to review how to prove these theorems, 332, 333, and 334, that will appear in a separate video. Have a great day.